Now that you've become more familiar with Unix commands, we can download an fMRI package and install it with Unix. If you haven't already downloaded FSL, watch this video. When you're done, come back to this tutorial. When you downloaded and installed FSL, you may have seen a few things you didn't completely understand. For example, if you go to your home directory and type cat.bashrc, you'll see this block of code. To understand what's going on here, you'll need to understand shells, paths, and variables. First, let's talk about shells. Think of the shell as an environment in which you can write Unix commands. We used a shell in previous tutorials, but you may not have been aware of it. When you open the terminal, it uses a shell to interpret what you're typing. Also, there are many different shells, and each one has a different syntax, or a specific way that the words in your command need to be organized, just like in human languages. For example, there are two major shells: the Bourne shell, with a widely used version called Bash or Born Again shell, and the C shells, with one popular variation called the T shell or TCSH. These commands we've used so far, cd, ls, pwd, and so on, are called built-in commands, and they can be used the same way in both shells. But there are important differences when you do a more advanced operation, such as setting a variable. Setting a variable, also known as variable assignment, takes a string and assigns it a value. The idea is to use the variable as shorthand for a value, and if necessary, update the variable as a script runs. For example, let's assign the value 3 to the variable x. If you are in the Bash shell, which is the default on most computers, you can do this by typing x equals 3, just like an algebra class. To check the value stored in the variable, type echo $x. The $sign is a reserved character that has a special meaning and cannot be used as a variable. The $sign indicates that what comes immediately after it, in this case x, is a variable. The command returns 3, the value stored in the variable x. Compare this with a different shell, the T shell. Switch your terminal to the T shell by typing TCSH and pressing enter. If we typed the same command as before, you'll get an error that says command not found. That's because the syntax for assigning a variable is different in the T shell. To do the same variable assignment, we have to type set x equals 3, then type echo $x to make sure it's set the correct value. If you want to know which shell you are currently in, type echo $0. Right now, we're in what is called a subshell. We were initially in the Bash shell, and then we switched to a T shell. When you open up a new terminal, think of that terminal as the Unix world. We call this world the environment. If we travel to different countries in the real world, usually the language is different. In Unix, that's like changing the shell and having a different syntax. But certain things remain constant, like gravity. If we wanted to have our x variable be the same no matter which shell that we're in, we would type export x3. In TCSH, we would type set env x3. Note that if you set this global variable, it's available only to the current shell and to subshells. If you set a global variable in the current subshell and then return to a previous shell by typing exit, you will not have access to it. To leave the current subshell and return to the previous shell, type exit and press enter. Now that we know what variables are, we can see how they are being used in the FSL setup. The code in the .bashrc file, which stands for bash run commands, and is the code that is run anytime you create a new shell in Bash, updates something called the path variable. The path variable is a list of directories that are searched anytime you try to run a command. You can see this list of directories by typing echo $path in all capitals. Your output may look different from mine since I've added more directories to my path. Notice that there are several absolute paths pointing to different directories, with the colon acting as a separator between paths. When you type a command and press enter, the shell looks for that command within each directory in your path. If it's not there, it returns an error saying that the command is not found. Paths allow you to use FSL commands from anywhere in the terminal. FSL, like all other software packages, has a library or directory that contains all of the functions needed to run FSL, such as FSL info, FSL maths, flirt, and so on. To run those commands, we would need to either be in that directory or we would need to specify the absolute path to the command that we want to run. To give us the flexibility to run FSL commands anywhere, we'll set the path variable to indicate where the FSL library is. Note that the FSL installation script automatically creates these paths in both Bash and TCSH. Other packages, such as AFNI and FreeSurfer, do not automatically create these paths, and you'll have to add the lines they give you, either using redirection or by opening up the run command files in a text editor, for example by typing open.bashrc. Now try the following exercises to review and consolidate what we've learned today. You'll need to understand variables in order to use for loops, which we'll talk about in the next video. When you start doing neuroimaging analysis, at some point you'll be using the same commands to analyze each subject, with only a slight alteration between each command. To save time, we will use something called a loop, also known as a for loop. Let's illustrate this with a simple example. Let's say that you need to print the numbers 1, 2, and 3. You could do this by typing echo 1 and hitting return, then echo 2 and echo 3. This gets the job done, but you can see that this would quickly become tedious if your goal was to print dozens or hundreds of numbers. How can we make this easier? You probably noticed that each time we ran the command, we changed the number after the echo command. Instead of doing this by hand each time, a for loop will run each command for you and automate it. Here's an example of a for loop to print the numbers 1, 2, and 3. You can also rewrite this as one line instead, with each part separated by semicolons. The semicolons divide the for loop into 3 sections. The first section is the declaration. It begins by assigning the first item after the word in to the variable I. In this case, it would assign the value 1 to I. The next section is the body, which runs the commands written after do, replacing the variable with whichever value is currently assigned to that variable. For the first loop, this will be the number 1. Since there are items remaining in the list, the loop goes back to the declaration and assigns the next number in the list to the variable I. In this case, now it's the number 2. Then the body is run again, and the process is repeated until the end of the list is reached. The last section, called the end, contains only the word done, which means exit the loop after all of the items in the list have been run through the body of the loop. You can add more commands to the body of the loop if they are separated with a semicolon. For example, we could change the loop to this, and the output would look like this. Eventually, we'll use for loops to analyze 26 subjects, with directories named sub01, sub02, sub03, all the way to sub26. For now, imagine that we simply want to print the name of each directory. Something like this would work, with the ellipses representing every subject name between 02 and 26, but it would be tedious to write out. You can make this more concise by using the seek command, or sequence, which prints every number in a range that you specify. For example, seek 1, 10 prints the numbers 1 through 10. We can include it in our for loop by using backticks, in which the command within the backticks is executed first and then expanded. This gets us closer to our goal, but it still isn't exactly what we want. Notice that the subject names we are trying to print should have two integers, such as O1, O2, O3, and so on, which ensures that each subject name is the same length. It also keeps them in order when they are listed with the ls command. This is called zero padding, and we can implement it in our for loop using the -w option in seek, which looks like this. This equalizes the width of each number that is printed. If it's a number less than 10, for example, it is zero padded with 1 0 to the left of the number. This will be important later on when we use for loops to analyze all of our subjects. Today we covered the basics of for loops. Later on, you'll learn how to use them in more sophisticated contexts, such as automating the analysis of an entire dataset. But no matter how complicated the analysis, every for loop is built on the fundamentals that you learned today. Try these exercises to further develop your understanding. At this point in the series, we're going to be using our Unix commands with fMRI data. Click on the link in the More Info box below for instructions about how to download the data, how to install FSL, and what skull stripping is. When you've finished, come back to this tutorial. The previous video on for loops showed us how to run many blocks of code with slight alterations between each execution. But what if we only want to run code if certain conditions are met? We can automate these decisions with conditional statements. If a certain condition is true, then do something. Else, if the condition is not true, then do something else. For example, we might want to check the anatomical directory for whether the anatomical image has been skull stripped. If it hasn't been skull stripped, then do the skull stripping. If it has been stripped, then do nothing. Try this on your own computer. First, navigate to the flanker directory, which in my case is on my desktop. Then navigate into the sub01 anatomical directory. From the command line, type the following conditional statement. As with the for loop, a conditional statement has three distinct sections. The first section begins with the word if, and then evaluates or checks whether the statement within the brackets is true or false. Within the brackets, the -e means check whether this file exists. If the file does exist, then the statement goes on to run the code in the body of the statement. You can have as many lines of code in the body as you want. The last line, fi, or if spelled backwards, ends the conditional statement. Note that if you typed out the conditional statement above, nothing happened. That's because in this case the statement was evaluated as false. The file doesn't exist, so the code wasn't run. If we want to do something in case the conditional statement is false, we need to add another section, an else section, which looks like this. This means that if this conditional statement is true, then run this block of code. If it isn't true, then run this block of code. Since the statement is false, the code in the else section is run. You can also check if a file doesn't exist by placing an exclamation mark before the -e option. At this point, I want to talk about common conditional statement errors. Usually this is because the syntax is off, and you should check it to see if the condition is formatted correctly. A typical error is not putting a space between the brackets, the exclamation mark, and the separate elements within the brackets. If you don't follow the syntax rules exactly, the conditional statement will throw an error. Let's finish with a demonstration of how to combine a for loop with a conditional statement. Let's say that we want to check whether subjects 1, 2, and 3 have a skull-stripped anatomical image. If it doesn't exist, Strip the skull using bet2. Navigate to the directory containing all of your subjects, and then run the following code, which you can also find in the More Info box down below. This will navigate into each subject's anatomical directory and check whether the skull strip image exists. If it doesn't, then it runs bet2 in order to skull strip the anatomical. The echo commands are optional. I like to include them so that the user knows which command is currently being run. We covered a lot of concepts in this tutorial, but time and practice will make you more familiar with how to integrate for loops and conditional statements into your code. Remember to check the links in the More Info box down below for more examples and exercises with conditional statements. The next tutorial will show you how to write all of these commands into a script, which makes your code more portable and easier to edit. See you then. You've learned many commands and concepts so far, which have enabled you to use Unix more fluently. The next step is to compile a group of commands into a single document called a script. Just as a movie script tells an actor what to do, where to go, and what to say, a Unix script, also known as a shell script, tells the terminal what commands to run. This makes it easier to edit and execute large blocks of code, and to move the code among different directories. Before we begin scripting, you should download an appropriate code editor. Windows users can download Notepad++, and Mac users should download TextWrangler. Once you've downloaded TextWrangler, open it and write this code on the first line. This line of code is called a shebang, and it means that the following code should be interpreted with the bash shell and follow bash syntax. Next, write one of the for loops you saw previously, such as this. It is good coding practice to indent the body of a for loop or a conditional statement, usually with a tab or a few spaces. This allows the eye to quickly see both the structure of the code and where certain commands are located. It is also helpful to include comments with the pound sign. Anything written after the pound sign will not be interpreted by the shell, but is useful for the reader to know what the command is doing. For example, before the loop, we could write a comment about how the following code will print the numbers 1 through 3. Now click on File, Save As, and call it printnums.sh, with the .sh extension signifying that the file is a shell script, and save it to the desktop. In a terminal, navigate to the desktop and then type bash printnums.sh to run the shell script. You could also run the command by typing /printnums.sh. This will run all of the code in the script just as if you had typed it out by hand. This is a simple example, but you can see how you can add as many lines of code as you want. Now let's see how we can run a larger, more useful script. Go to this link, and then click on makefsltimings.sh. Click on the raw button to see the raw text. You can either right-click anywhere on the page and save it as a script, or you can copy and paste the code into TextWrangler. Once you've done that, save it as makefsltimings.sh and put it in the flanker directory. Let's take a look at what this code does. Notice that we have a shebang indicating that the script is written in bash. We also have comments after each pound sign marking the major sections of code. The first block of code is a conditional statement that checks whether a file called subjlist exists. If it doesn't, then list each subject's directory and redirect those names into a file called subjectlist.txt. This brings up an important concept: wildcards. There are two types of wildcards you will often use. The first is an asterisk, which looks for one or more characters, and the second is a question mark, which matches a single character. To see how this works, navigate to the flanker directory and then type makedir sub-100. If you type ls-d sub dash asterisk, it will return every directory that starts with sub dash, whether it is sub 01 or sub 100. The asterisk wildcard doesn't discriminate whether the directory is 6 characters long or 600. It will match and return all of them, as long as they start with sub dash. The other type of wildcard is the question mark, which matches a single occurrence of any character. If you type ls-d sub-2 question marks, it will only return directories with 2 integers after the dash. In other words, it will return sub 01 through sub 26, but not sub 100. The body of the for loop contains another thing that is new, a command called awk. Awk is a text processing command that prints columns from a text file. It is a complex command, and we won't go into all the details, but here are the basics about how it works. If you go into a subject's func directory and type cat, one of the tsv files, it will return all of the text in that file. For our fMRI analysis, we want the columns that specify the onset time and duration, as well as the number 1 as a placeholder in the last column. You can redirect the output of this command into the input for the awk command by using a vertical pipe. Then you can use conditional statements in awk to print the onset times for specific experimental conditions and redirect that output into a corresponding text file. This is discussed in more detail in the book chapter in the link below. Now navigate back to the directory containing all of the subjects, remove the sub 100 directory, and then run the script. It will take a few moments, but it will create timing files for all of your subjects. You can inspect them by going into each subject's func directory and use the cat command. Each one should have 3 columns, and they should look something like this.